Okay, let's talk about acids and bases. Acids were originally defined as something that tastes sour. Now, obviously, going around and tasting a bunch of acids is not the best way to determine if you're dealing with an acid or not. So, chemists came along and defined an acid as something that has an ionizable hydrogen. And when we say ionizable hydrogen, we mean H plus in solution. Now, ionizable hydrogen in solution just means that when the acid dissolves or when the substance dissolves in water, H plus is a product. For this class, you just need to be able to recognize an acid, and you can do that because the molecular formula starts with H. An example might be HCl. I know that's an acid because it starts with H. H2SO4. I know that's an acid because it starts with H. Something that starts with acid or starts with hydrogen that is not an acid is water. Water is not an acid even though it starts with hydrogen. So just be aware of that. Some other properties of acids are that they are electrolytes. We talked about the types of electrolytes they can be. They turn blue litmus paper red. They can react with metals to form hydrogen gas. And they also neutralize bases in neutralization reactions. We have two different types of acids that we talk about. We have a strong acid, which completely dissociates or breaks up when dissolved in water. For this class, we are going to talk about six strong acids, and you need to know these strong acids. They are hydrochloric acid, hydrobromic acid, and hydroiodic acid. Notice these are all the halogens, with the exception of fluorine. HF, hydrofluoric acid, is not a strong acid. It is a weak acid because that H plus and F minus are going to be really strongly attracted to each other and they're going to get back together. So they do not completely dissociate in water. Our other strong acids are sulfuric acid, H2SO4, nitric acid, HNO3, and perchloric acid, HClO4. So these are the strong acids for this class. Keep in mind there are other strong acids, but we're just not going to talk about those in this class. Weak acids do not completely dissociate in water. They only partially dissociate or they partially break up when they are dissolved in water. So some examples of weak acids that we might have heard of before is acetic acid, also known as vinegar, phosphoric acid. Phosphoric acid can be found in a lot of sodas. Hydrofluoric acid. These are all examples of weak acids. Essentially, if it's not a strong acid, it's a weak acid. All right. So if you just remember all six of the strong acids, then you're essentially remembering all of the weak acids as well. Because if it's not on this list, then it's a weak acid. Bases Or any compound that has an ionizable hydroxide in solution. So an ionizable hydroxide in solution just means that you have OH. So it produces OH in solution. And remember, in solution just means when it's dissolved in water. So here, for this class, you are going to recognize it because it's going to be a soluble ionic compound containing hydroxide, containing OH. And if you think about this, our acid, our acid has H plus and our base has OH minus. So if we look at our acid-base chemistry, then we can neutralize the acid and the base and make water out of them. So bases were originally defined as something that tastes bitter. Obviously, again, not a great idea. They also feel very slippery. They feel almost soapy. That is the base reacting with the skin cells and salts on your hand, and your cells are coming off. They can also be electrolytes. They turn red litmus paper blue, and they do react with acids. So here are some examples of bases. So a lot of cleaning agents are bases. Just like with acids, we have different base strengths. So strong bases completely dissociate or break up when dissolved in water. We also have 6 strong bases for this class. So we have lithium hydroxide, sodium hydroxide, and potassium hydroxide. Technically, cesium hydroxide is also a strong base because it is in group 1, so it is a soluble hydroxide. However, it's just not nearly as common, so we don't talk about it a whole lot. And then we have calcium hydroxide, strontium hydroxide. My pen is freaking out. Strontium hydroxide and barium hydroxide. So these are the 6 strong bases. And you got it. We also have weak bases. Weak bases, just like weak acids, partially break up. They partially dissociate when they are dissolved in water. So some examples of weak bases. Ammonia is a really good example, and a lot of people will think that's a strong base, but it is not. Bicarbonate, you used that to neutralize the vinegar in your lab. So that is another example of a weak base. Now, just like with the strong acids, if you remember the strong bases, then you know all of the weak bases. Because if it's not a strong base, it's got to be a weak base. So here are some examples of bases and their common uses. Now, soap is a reaction between an acid and a base. And soap is super, super cool because if you think about it, we learned that like dissolves like. So polar molecules dissolve something polar. Nonpolar molecules dissolve something that is nonpolar. Well, water is very polar. And so when you're trying to scrub your greasy dishes, a lot of times it just doesn't work. So we'll use hot water, which will increase solubility of that grease, but we also use soap because the grease will be soluble in soap. So we use a process called saponification. And it is a chemical reaction between a strong base. Usually we use lye, which is sodium hydroxide, and it's going to react with some sort of oil or fat to make soap. So here is an oil or a fat. It's actually a compound that has these functional groups right here, which are called esters. And you react it with sodium chloride or sodium hydroxide, and we make soap. Now, the thing that makes soap so unique is it has this polar head right here, followed by a nonpolar tail. So, soap is soluble in both water and grease. So, you can put that soap on your grease. That grease is going to become soluble in the soap. It'll come off your dishes, but the soap remains soluble in water and will take it down the drain with the water. Here's a space filling molecule. So here is just our nonpolar tail. Then we can add the hydroxide there and form this polar head. And notice that these water molecules are going to surround it with the hydrogen facing in, and it can dissolve that grease.